Okay, it's time to start. It's my great pleasure to introduce Kathleen McKeown. She's a Henry and Gertrude Rothschild Professor of Computer Science at Columbia University. She's one of the central figures in the field of natural language processing and computational linguistics. Her research focuses on text summarization, natural language generation, and on analysis of social media. Kathleen has been recognized for her great work by various awards, which I cannot list here, but they include an SF Presidential Young Investigator Award in her early career, and more recently by Anita Borg Woman of Vision Award for Innovation, and many others. She is a AAAI Fellow, an ACM Fellow, and one of the founding fellows of the Association for Computational Linguistics. Kathleen is also a founding director of the Data Science Institute at Columbia, which was launched in 2012, so it's a bit older than the statistics at MIT, or at least the Statistics Center at MIT, but we're catching up, and we're happy to have you, and please welcome Kathleen.
Hey, thank you, Sasha, for that introduction, and thank you so much for inviting me here today to speak. We all know about the large amount of text that is available on the web, and in our research, in my research group at Columbia, we're looking at how we can take advantage of that text to address some societal challenges. And so I'm going to be talking today about several applications in this space that we've been working on over the last 5 years or so. So my research fits within the Data Science Institute. The Institute has multiple centers, and the center where I am most relevant is the Center for Data, Media, and Society. And here we're interested in how we can develop the tools that are needed to enhance communication and interaction within communities. The vision of my work is in generating presentations that connect events, opinions, personal accounts, and their impact on the world. And I'm also working on the analysis of social media in order to gain insights into events in the world. We take a machine learning approach in our work. So we start with data, which is often labeled. We extract features from the text data, and this is where natural language can come in. And then we use the machine learning to predict output. Now, I don't do research in the machine learning algorithms themselves, so what I'm interested in is what data is available for learning and what features can yield good predictions. So I'm going to be talking today about our work in a number of different genres, and they span a continuum from objective to personal. And as we go from the top to the bottom, we have genres that deal more or less with fact. And as we come down, we have genres that are much more subjective in nature, opinions may be expressed, and so forth. So today I'm going to be talking about our work with news, personal narrative, social media, and I'll end with relatively new work on analysis of posts by gang-involved youths in Chicago. So let's start with news. Now, in the natural language community, we have, since the 90s, had very large corpora of news that are annotated with information that has enabled the development of core NLP technology, such as part-of-speech taggers and parsers. And these, in turn, have enabled the development of technology, the kinds of applications that I'm going to be talking about today. We depend on them. So in news, in the area of news, we began with summarization. And one problem that really interested my students was being able to provide objective updates during disaster. And we were motivated to begin this work after Hurricane Sandy hit New York. And you know, all of us were huddled in our apartments and looking at who was safe and who was not. Many of the students were in these red areas in Brooklyn. And so this is how we started. So the system that we have developed and are working on is one to monitor events over time. As input, we take streaming data, and this can be news or web pages. And at every hour, we want to generate a summary, which is an update on what's new. So our ultimate goal, our vision, would be when an event, major event, occurs, to be able to track that event over time and to be able to identify sub-events that it spawns. For example, the Manhattan blackout, the Breezy Point fire, or the public transit outage. So the data that we're using for this work is data that NIST collected for a similar type of problem. And this consists of a web crawl from 2 years, 2011 to 2013, in the areas of disaster. And they have 11 categories of disaster. So shown here are just some of them. So for example, protests, terrorist events, bombings, and so forth. So our goal is to be able to take a stream of information, and we're looking at now at data from this web crawl. So this is an earthquake in Guatemala, and over the course of an hour, we would take in all documents. I'm showing only 4. There are many, many more. And to generate a short update at the end of the hour here, for the first hour, it would present the most salient information about the earthquake, where it hit, the magnitude of the quake, and so forth. Of course, at hour 2, we have to be careful in presenting new information. We do not want to repeat what we said at hour 1. All right, what has happened here? I hope you can restart. Okay. I hope that wasn't something I did. All right. So as an algorithm, we're using an approach called temporal summarization, where at every time slice t, and we're working in time slices of an hour, we want to predict salience for the input sentences that come in that stream during that amount of time. And here we're looking at making use of disaster-specific features that can help us more accurately identify what is important. We then remove redundant information, so we look back at what we've already presented. We still have a very large amount, and so we cluster, and the cluster should represent a topic, a coherent topic, and we select an exemplar sentence for time t from each cluster. Or for our clustering algorithm, we incorporate the salience prediction as a prior, so that helps. So what kind of features do we use in predicting salience? One is language models. So these are models of the frequency with which we would see unigrams, bigrams, common two-word sequences, trigrams, and so forth. We use a generic language model 10 years from the AP and New York Times, and this kind of model would score sentences to tell us how typical they are of the language in general. So they are helpful. If we get a higher score, it tells us that we have a more fluent sentence. And since some of our sentences are coming off the web, that's important. We've also built some domain-specific language models. We use Wikipedia and the disaster-related Wikipedia articles. So for each category that we have, we build a separate language model. We have one for earthquakes, one for hurricanes, one for terrorist events, and so forth. And a domain-specific model will score a sentence by how typical they are of the particular disaster type. So again, that can let us identify sentences that are important for what we're looking at. So if we look at these 3 example sentences that come through to us for the Guatemala earthquake with our domain-specific corpus, it will give a higher score to the one at the top. It has bigrams in it that are typical of earthquakes, like disaster management or local tsunami alert. We're also using geographic features. So we don't want to get sentences that are typical of any earthquake and risk retrieving a sentence not related to the current one. So we tag the input with a named entity tagger. And then we get coordinates for locations and their mean distance to events. So this can help us identify sentences which are referring to things which happen closer to the center of the disaster. So here, both of these sentences would receive a score, but the top one would be higher. And then we also make use of information about semantics. So we make use of synonyms, hypernyms, and hyponyms. And so shown here, disaster is a hypernym of earthquake, so it would, again, get a higher score. So what have we learned here? Well, we've experimented with our system, which is shown in red, our system without the salience predictions, which is shown in blue, and then 2 other state-of-the-art methods for doing summarization. The top shows precision, the bottom shows recall, and the x-axis shows time. And we can see that on the top chart that the salience predictions lead to high precision much more quickly than the other algorithms. And we can also see on the bottom chart that they allow us to cover more information more quickly, not as quickly as the rise in precision, but we still have one. So what's next? This work was done not too long ago, maybe 3 years ago. And you can see the dramatic change in the field of natural language. We are now moving to neural nets. So we're experimenting with neural nets for summarization updates. And we're looking at new models that we can use for generation so that we're not simply extracting sentences. Okay, so let me move now to our work on personal narrative. And I use here as an example the autobiography of Malcolm X. This is told from a personal point of view. It's a story that he is telling to us. And it has some very compelling sort of life and death moments. And that's what we're interested in looking at. Of course, we're not going to be looking at something as long as an autobiography. So how is personal narrative different from news? Well, first, we have a coherent telling of a story. And that story has what we're calling this compelling component, a life and death point in the narrator's life, a reason for telling the story. It's usually a monologue. And it also, since we're finding it on the web, is much more informal language than we have in news. We're also using it in the context of disaster because we'd like to be able to pick out personal stories about what has happened to individuals during the disaster and be able to summarize those as well. So an example here of the kind of online, this is a blog, personal narrative that we found online that has to do with Hurricane Sandy. So this is an example of what we want. And you can see that it starts out with background. We were sitting down to a late dinner on Monday night when the storm was supposed to hit. It was incredibly windy, but the rain really hadn't been that bad. And then the story moves on to a series of complicating actions. By 10 p.m., the skies lit up in a purple, blue, and blue brilliance. The power started to go out here and there. That's when I noticed neighbors across the street running out of their homes and fire trucks racing down the block. I saw a trickle of steady water coming down the street on both sides, and then water began pouring in through the creaks in the basement door. So my husband went to grab the pump. And here's where we have what we're calling the reportable event, that moment of life and death. He went upstairs to get a tool, and in those few seconds, ocean waves broke the steel door lock and flooded the basement 6 feet high in minutes. So our goal in looking at these narratives is to be able to identify the sentences which convey the compelling event. And we hypothesized that this reportable event could then serve as a summary for what is this story about. And we envision a sort of interface where we have the summary of objective events as it unfolds, as well as personal experiences. Now, data. We did not have, as in the other case, a lot of data which had already been labeled by NIST. So we were creative, or the student, I should say, was very creative in looking at what kind of data we could use. And so she used a subreddit of Ask Reddit called What's Your Creepiest Real Life Story? We downloaded 3,000 stories from that. Of course, we could get any amount as we kept going. And there was some amount of work in doing this to ensure that what she got was really a story. Then we had a small amount of that manually labeled. So we had some of our friendly graduate students labeled some of the stories to identify where the most reportable event was. And of course, that was small. We had like on the order of 300 of these. But then we could have a very large amount of the remaining stories automatically labeled using distance supervision. So what did we use? We used a variety of different kinds of heuristics, which we thought we could help. For example, TLDR, if the story had one, we thought would be a good summary. And if we could find the relationship between that and sentences, that might label for us where the most reportable event was. We also use comments, hypothesizing that more comments would be about this point in the story, and that might help us. Of course, these are noisy labels, so one of the things we have to look at is, does that help or hurt? We then turn to linguistic theory in terms of what kind of features we could use for identifying the most reportable event. And we built on Prince, Gerald Prince from Penn, who writes that stories are about change, to Livia Poliani, who noted that the turning point in a story is marked by a change in formality, style, or emphasis. And to William Labov, who the structure that we've been using to annotate the stories comes from him, noted that a change in verb tense often accompanies the most reportable event. So we thought, well, what kinds of changes could we measure across the story? And so we looked at what kinds of scores we could develop for each sentence. And so we looked at syntactic scores. One very simple one is sentence length, hypothesizing that at that dramatic point, it's going to change, perhaps be quite short if everything else has been long, or the reverse. We looked also at statistics about the parse trees. We looked at semantic information, so how similar was a sentence to surrounding sentences, again, hypothesizing that there would be a change at the most reportable event. And then we looked at affect, so how pleasant are the words, or how unpleasant or negative. activeness, how intense are the words that are being used, or imagery, how concrete are the words in terms of what they refer to. And to get these scores, we use the Dictionary of Affect and Language, which for each word has these 3 different dimensions with scores. So you can see a graph here of the sentence, and this one just shows activeness and pleasantness. And we hypothesized that the most reportable event would likely occur at a max or a min in these scores. So shown here, it occurs at a min in pleasantness and a max in activeness. So we had many of these scores, and we developed a support vector machine approach to do learning over this. I've talked about the change features, but we had, of course, many other features, ones that are standardly used, like engrams, part-of-speech tags, and so forth. And what we found was that the change features are the most effective in being able to pinpoint where the most reportable event is. We also experimented with different ways in which to use the data. So we tried the seed data only, which is a very small amount of labeled data, but it's accurate. With distance supervision only, which is large but very noisy. And then we tried a self-training approach where we started off training on the seed data, and we used the predictions of the trained system to feed back as labels, but only when they match the distance supervision. So it was sort of a combination of both, and you can see that the self-training did the best. This is a hard problem, and it's one we continue to work on. So what's next? We're even more so in this domain where we have very informal text, a lot of pronouns. Often the extracted sentences standing alone don't make a lot of sense. So we're looking at how we can rewrite the extracted summaries. And to do that, we first built a corpus that pairs extractive with abstractive summaries that people have written that rewrite the input. And we have developed a method which allows alignment between the two. And then we can use that aligned data to learn a model for revision operators. And we're starting off by looking at revision operators for paraphrasing. Okay, I'm going to take a brief tour into social media. So how is social media different? It is also informal languages. But it contains many subjective expressions of feeling, sentiment, and emotion. And if we're looking at Twitter in particular, we have short, isolated comments. So we're also working as part of a project where we're looking at how we can make use of social media to help in disasters really around the world. And so we see here a picture from an earthquake in Nepal, another disaster that occurred in West Africa. And one of the first things we can see is that disasters don't always occur where the main language is English. So what we're looking at is, can we analyze the subjective posts of everyday people in the language that they speak, so around the world and in different areas where perhaps we don't have machine translation that works well yet. And we're looking at whether we can identify sentiment and emotion in these low-resource languages. And the idea is that if we can, and we identify much negative emotion, this would be an indicator of where problems still persist, particularly if we can tell what the negative emotion is about. So we've been experimenting with this problem. We have, for years, worked on sentiment analysis in English. And the question we had was, could we create sentiment analysis systems for other languages without using machine translation. And so we did an experiment where we had 16 different languages. We leveraged different amounts of parallel and comparable corpora. So parallel corpus would be where you have a line, the English and the foreign language. Comparable is where you have English and the foreign language on a similar topic, but not necessarily translations of each other. We experimented with different transfer model scenarios, so whether we transferred from a single source or from multiple sources. So do we do the transfer just from English or from multiple languages? And then we looked at two different models for transfer: projection of source language annotations, so these would be from English, and then what we call direct transfer of source language models. So in annotation projection, we start off, we have a sentiment system that works in English. We tag the English side, so we can see on the bottom of our parallel corpora, maybe relatively small, with our sentiment system. And then we transfer those tags from English to the foreign language. We could also use multi-source projection. If we have systems running in different languages, we'll transfer from multiple of them into the target language. And then we use a majority vote to decide on the label. In direct transfer, we do things a little bit differently. We train a model on the source language and apply it directly to the target language. And how do we do that? We do that in two ways. First, we use word representation features. These are cross-lingual word representations. And then we also use lexicalization with code switching. So from the parallel data that we have, we create translation dictionaries. So for each of the words, this will give us potential translations. They may not be accurate. And then we have we may have a large amount, much larger amount than parallel data of monolingual text. And we translate as many words as possible that we can to the target language or to the source language, either way. And we end up with what we call a code switch language. Some of it is in English, some of it is in the foreign language. And because some of it is in English, we can apply our labels there, and when we train, it will automatically carry over to the foreign language. So this gives you an idea. We're using bidirectional LSTM. And what you can see at the bottom, which is interesting, is the code switch language here. So we have, I guess this is German, and we have, for the first word, it's translated, the second word it is, but we have some words that aren't translated and appear as English. So in our experimental settings, to see how these approaches work, here are our 16 languages. Some of them are more low resource than others, but they're ones in which we could get parallel data. So Arabic, Bulgarian, Chinese, Croatian, English, German, Hungarian, Persian, Polish, Portuguese, Russian, Slovak, Slovene, Spanish, Swedish, and Uyghur. So we need the parallel data either to do the projection in our projection approach, or to build the cross-lingual word embeddings, and to build the dictionary translation in our direct transfer approach. So the question is, with how much data and what kind of data, how well can we do? So of course, we have the Bible and the Quran, which is available for all of these languages, and we have lots of data. But it's very much out of domain. It's, we're not going to be seeing the same kind of words that we see there as we do in the Twitter that we're trying to tag. We do have it for all 16 languages. Slightly better is Europarl. It is multi-parallel. It's political text, so it's a little bit closer to what we want to deal with. We have it for 10 European languages, so not as much for some of the lower resource languages. And then we have data that was provided by the Linguistic Data Consortium at Penn. This has been a fantastic resource for providing annotated data for our community. And in this one, we have the English only in one language, so it's not multi-parallel. It's very much in domain, but we have it for a smaller number of languages. And I'm not going to, there are many results. I chose not to show the tables. I wasn't sure what kind of audience I would have. I could see that it would have been OK to have tables for you guys. But so I'm just giving the high-level results. The genre. As expected, the in-domain data is best. It enables significant increases in performances for most languages. But again, we don't have it for all languages. If we look at projection versus direct transfer, it was interesting. In the single source case, they're pretty equivalent. In some cases, one was better, in some cases, the other. It was hard to tell when. But if we use multi-source models, then the direct transfer is better. Nonetheless, for some non-Indo-European language families, projection does better. And again, it may depend on the similarity between the languages or the amount of data. Code switching, this method that I talked about, was essential for the performance of direct transfer. When you drop it, performance drops. And then using multi-source gives a clear advantage over single source. Okay, so I'm going to be turning now to the last area that we're studying. And, well, you will see that these posts are very different from the kind of language that we see most of the time. They're informal. There's a lot of slang. There is dialogue, so we have back and forth between people. The data set that we're looking at is Twitter, so each contribution is short. And this is what I would call a true data science project. It is a collaboration between computer science and social work. The social work faculty's name is Desmond Patton, and when he arrived at Columbia, he came to me and said, I'm working on a problem, and I'd like to engage somebody from computer science or data science to help out. So he was looking at the problem of firearm-related deaths, which is, as we all know, a big public health issue in the US. And the violence that comes from this disproportionately impacts low-income cities. So if you look at Chicago, Chicago had more than 3,000 shooting victims in 2015. And what Desmond had noticed is that violence is exacerbated by taunting between gang members on social media. And he termed this the digital street and was studying the digital street and how it mapped to life on the physical street. And he was working with a case study. This is a young woman named Jakira Barnes. Jakira joined a gang when she was age 13 when a friend of hers was shot and killed. And this is a common occurrence. People experience a lot of trauma when friends and family members are killed, and this can be the trigger for later action. So it was unusual. She was known as a shooter, one of a few female shooters. And she was also very prolific on social media. So she was, and I have to say she was in turn shot and killed at age 17. So in this period of her life, she had some 3,000 posts and 42,000 followers. So it's this data that we're looking at. This gives you an example of the language and what it looks like. And one of the things that we found was computer scientists could not do this alone. We do not understand the language and what is being referred to. For example, in the top one, deframe, I didn't initially know what that is. That is the viewfinder of a gun. The bottom one, so O-Block was Chikaira's gang. These are often named after the streets on which they live on. Desmond and his group had collected a large amount of this data, and they had an annotation. They have an annotation team, and they were doing what they call qualitative annotation. They make a lot of use of the context, and this consists of social work researchers in the social work school there, and as well they have connections with Chicago youth who have a lot of experience with the language. And we had a lot of interaction back and forth between this group and the computer scientists, both in terms of what we could do and what we needed. And they have been and continue to label the tweets of Chikaira and her followers, and we're continuing on. They use what's called a deep read, where they want to relate what they're seeing in the tweets to external events, so that we have a match between expressed events and external events. So this gives you an idea of the labeling. The top two are labeled as aggression, and they have a more fine-grained label of threat or insult, and the bottom one is labeled as loss. So this is also common to have much expression of loss after trauma on social media. So these are the themes that were emerged: aggression, loss, and other, and again, different types, but our algorithms at this point could not, we were going to be lucky if we could handle, just a few categories. But you can see how the fine-grained ones collapse into more coarse-grained categories. And of course, there are a large number of other tweets, which are just general conversations, and they also represent points of happiness. So on the natural language side, we've experimented with two different methods, two different systems. One is a more traditional supervised system where we extract discrete features and we feed it into a support vector machine. The second is more recent. It is, we're looking at a semi-supervised approach because there's a smaller amount of labeled data, and can we make use of this very large amount of unlabeled data? And we thought, given the promise of neural nets, we might be able to achieve higher accuracy with that. On the supervised side, one of the first things we had to do was to build a part-of-speech tagger for the data so that we could know that a word like op is a noun and smoke is a verb. We also developed a bilingual dictionary, which we did by glossing a set of the tweets into standard American English and then using machine translation tools to align the two. And that gave us a phrase book, which we could use so we could make use of other kinds of resources. And then the features that we used, again, the Dictionary of Affect and Language, which we used before. We thought emotion would be a definite indicator of what was happening. We also made use of the part-of-speech tags and then n-grams, and we used both words and emojis. And then we used the cascaded SVM classifier, two binary ones. The first one separated out aggression and loss from other, and the second one divided between aggression and loss in that subset. On the semi-supervised approach, we thought, well, we really have a large corpus of unlabeled tweets. Certainly, we should be able to take advantage of them. And we tried two different methods. The first one, we used distant labeling, so somewhat similar to the previous project. We looked at the two emojis that were most highly correlated with loss and aggression, and we used those to label additional data. And then we trained on that and used that as initialization for our supervised neural net system. Then we also used a new method, which we call convolutional filter pre-training. And the idea here was to find in all of these unlabeled tweets to encode each tweet as a vector which was predictive of tweet words that are highly correlated with either aggression or loss. And again, we use that to initialize the neural net. For the neural net, we used a fairly standard convolutional neural net, and we experimented with one at the word level and at the character level. Words were initialized with word to vec, and characters were randomly initialized. We did tune the vectors during training. We kept certain kinds of symbols out, so hashtags were kept intact, but we removed URLs and retweets. Each emoji was treated as either a single word or a character, depending on which CNN we were using. So this gives you an idea of the architecture with the embedding dimension of 256, a convolution with filter size 5 and 200 feature maps, pooling over time, fed into a softmax classifier. The label data that we had was close to 6,000 labeled tweets, but you can see it's somewhat problematic because it's very unbalanced. So a very few amount of aggression tweets, more loss, but a large number of other tweets. With the distant labels, we could get an additional 51,000 labeled. For CFP, we removed extremely short tweets, and that left us with 600,000. So it enabled the use of a far larger set. These are our results. Sort of interesting because the SVM was very hard to beat. So you can see the individual CNNs did not do that. They're very close. When we use the distantly supervised data, we go very slightly better, no real difference. In the green, when we look at the new method, there we do see a jump up. But when we ensembled the distantly labeled character level 1 with the CFP, because we saw that the character level 1 and the word level 1 could identify different things, then we get a much higher jump, up to 71. So what have we learned here? The first is that collaboration across the disciplines is essential. We would not have been able to do the work without it. In the annotation group, or the group that was studying the tweets themselves, they saw context as really critical. And in fact, often when we had an error in our classifier and we thought, oh, the label has to be wrong, and we would go back and they would say, oh no, that's referring back to an event that happened back here, and there's absolutely no way we could have seen it. So we're beginning to look at how we can make use of context rather than dealing with each tweet individually. There's another group at Columbia led by Shifu Chang who's doing the same kind of work, but with the images that appear. And we have just begun work on merging our image output with our language output. So I hope to have shown you how we can make use of data science techniques in a wide variety of different kinds of genres. And that to do so, we need to take information from different kinds of sources for natural language, from semantics, pragmatics, to real-world context, and all as part of machine learning. I want to acknowledge the work of my current students who were critical in getting this done, and as well the work of my past students on which much of the work is based. So thank you.
Thank you for a wonderful talk. We have a few questions.
It's very rare to see a survey this inclusive, so I appreciate you going through it. I have two questions. These are a little bit in the weeds, but when you were talking about the reportable events, you said that there were three categories: syntactic, semantic, and affect. Do you know how much? I guess if I were to train a model that was only using the syntactic features that you described, right? That would be the simplest thing that I could create. What would my performance look like? Did you do something like that?
Yeah, I mean, we looked at the difference between these different features, and so we did feature selection, and the one with the most impact is the change features. I don't have off the top of my head how much of a difference that was, but yeah, you definitely saw a significant increase when you included the change features.
The change features applied to each of those, or was it?
Sorry, when you included the affect. Yeah.
Okay, the affect.
Oh, okay. So you're asking about what if I just use the syntactic ones?
Right.
Yeah, no, I don't think you would get a really strong performance. And we did look at the different variations, but again, I can't tell you the difference.
Yeah. And one more question on the Twitter. Once upon a time, I did similar analyses, and almost the entire performance of the model was based off of the emojis. Did you do an analysis using and not using emojis, or what proportion of the tweets had or did not have emojis in them?
So, yeah, again, you're asking for numbers that I don't have. The emojis alone would not get you there. We did look at, for example, if you could predict the emojis from the text. Again, could you use that as a pre-training filter? And we're just in the beginning of those experiments. I will say, so this may answer your question because this is even more recent work, that when we did do fusion between the text and the image side of things. And when we did the fusion of the two, we got a tremendous boost in accuracy of about, well, there we were measuring using a slightly different measure, but of about 10 points. So we can see that using different modalities is really helpful. Yes?
My question was about temporal issues with the tweets. Did you notice any strong correlations between aggressive tweets happened in rapid succession versus others, or anything, patterns like that?
So that's something that we're beginning to look at now. This is very much ongoing work. Desmond and colleagues have a paper out recently which shows a correlation between a higher number of aggressive tweets following loss, which indicate, sort of boost the hypothesis that which they were seeing through manual annotation, that when there's a post about loss, it can be followed with retribution and ultimately aggression and threats. And so they did see a pattern there. It's hard to get, so we've done a lot of looking at patterns across time. The problem is that the amount of posts that are aggressive are relatively low. So when you're now looking across time, you have even more of a sparse data issue. So it's hard to get a pattern that's really significant out of there otherwise. But we have been looking at how previous conversations impact what comes later, and the words that are used and the emotions that are expressed.
Hi, just to follow up to the previous thing, probably the data imbalance that you're talking about, the numbers that you showed, if I remember correctly, they are in 800s and 400s when it comes to aggression and loss, and there's a huge percentage which is others. Have you looked at the data more closely? What does that other category consist of? And precisely because we see that sort of imbalance, does it make you at any point question the hypothesis that there might be an inherent correlation between aggression and the prediction that you're going for?
Well, it makes it a harder problem because we have imbalanced data, but that's often what we have in the real world. And in fact, many of the problems that we look at have that problem. We have begun to look at other categories within other. For example, one of them is substance abuse. And substance abuse, this is another activity that is highly tweeted about. And substance abuse can also be a predictor of later instances of aggression. So, you know, I think, again, the work is very early, and we'll be looking at these, you know, these other categories. I mean, the question that we are working with community outreach groups, and the goal is if we have a system like this, it could be used to inform community outreach groups you know, when there is either a loss being posted, there are groups that work with them on different ways of handling grief, or a post about aggression to intervene before something happens. And they already search social media manually. This is one of the ways that they work, but it's very hard with the large amount of data that's out there. So I think it's a valid approach to the problem, you know, but the large category of other does tell us that, you know, there are many good things going on as well.
Hello, thank you for the great talk. So when it comes to the reportable news, I wonder if the language, the inconsistent use of language has ever confused the training algorithms and the classifiers, because, for example, the National Weather Service has their own definition of advisory, warning, and watch, which may be different from our own understanding of what those words mean. So they have certainly confused human beings. So I wonder if they have ever confused the classifiers. Thank you.
Well, that's a level of analysis that we haven't done, but it would certainly be something that we could look at. Yeah.
Whether you compared that against terrorist Twitter accounts and like Boko Haram or ISIL?
So, you know,
the question?
Oh, so the question was, he's wondering whether the Twitter analysis that we do with gangs could also be appropriate or applied to any terrorist groups like Boko Haram or so we're still so early in it. It's, you know, we think it could be, but the question is what kind of language is being used, you know, by these groups, and do we also have to make use of some of our foreign language work in doing it? You know, how much is going on in English, is a subdialect of English. So I think the overall technique holds some promise for doing that, but you know, I don't think I could make any claims at this point about whether it would or would not work.
Great talk, by the way. In your first part and the third part of your presentation, both were about events that were about disasters. And one was the news source, the other one was social media source. Again, in both settings, you have time-stamped information as well as geolocation stamped information. So is there a hope to stitch those two things together to get something better?
There certainly would be. And I think that's, you know, so my work in it has happened in separate programs, like the news and the personal views was funded by NSF. The Twitter and sentiment is funded by DARPA. And in the DARPA program, they have a lot of people working on this, looking at different kinds of news sources and how we can bring them together. So where sentiment is part of it, they're doing more work on extraction of entities and events from the news. So yeah, I think you should be able to use both.
Okay, let's thank Kathleen again for a wonderful talk. Thanks.